Yeah,
So,
okay.
okay, so today we have Adele talking about the unitary Fermi gas.
Yeah, so the Unitary Fermi gas. So it's very general title, should be very much understandable for experimentalists and theories. So I will do like 15 minutes introduction, very general concept, understand this Unitary Fermi gas and how interesting it is. And I think that's a perfect system for experimentalists and theorists. Um, so my guideline for the first part is what do neutron stars, metal, and nuclei atom have in common? So that's the question I like to answer. And for that, I will really go back to the origin of physics and the quantum nature of bosons and fermions and the difference in the statistics. So here you have from this paper, you have the reference here. So for the moment, we don't really care about how they did the experiments, but you have bosons. So here they use like lithium-7, they use lithium-6 atoms, and you can see that as you cool down your system, the cloud for the bosons shrinks, but not for the fermions. Like it shrinks a little bit, but then it looks like it stagnates to a certain side, and it's an evidence like of Fermi pressure. And we can understand that from the boson to fermion statistics because bosons can go in the same energy level and at zero temperature they will all go into ground state and undergo Bose-Einstein condensation below a certain critical temperature. But fermion, they will just fill the energy level until the last one that we call the Fermi level, and so we will be more in the presence of a Fermi sea. So it looks like for fermions, nothing really interesting happened at low temperature. So to complexify a little bit the system, we can have two component fermions. So what do I mean by that? Is more spin up, spin down. So electrons, or for our lithium-6 atom, it will be two hyperthin states. So we can populate two hyperthin states in the experiment, or neutron spin up, spin down. Anything that modelize spin up, spin down. And if we turn on interaction, we can have two different configurations. So either the two fermions form a bound state, so they will form a molecule, but it's still nothing much different from a Bose-Einstein condensation with lithium-7 atom, because atom are composite particle. Here it's just a molecule. So we know they will undergo like Bose-Einstein condensation. But there is another type of pairing that is interesting is when you're in the presence of a Fermi sea, you can have, when you have a small attractive interaction between a fermion, they will form a weakly bound state. So we cannot talk about molecule anymore, but there's still boson. And so this is a theory of Bardeen, Cooper, and Schrieffer of superconductivity. But the origin is very different. It's like a many-body physics effect because we need the presence of this Fermi sea. And on the first case, it was more like a bound state formation. But both situations like bosons, so they will condense, so microscopically occupy the lowest energy level. So people study this very differently, like BCS and BC was studied for different effects, but then people understood it was just part of the same picture if you modelize the interaction between the fermions at low energy with the scattering length. So that's the only parameter you need to explain the potential between the two fermions. So it has unit of length, and the other scale that you have in your system is the Fermi momentum, and so that's the dimensionless quantity you can build. So I will more be talking about 1 over kFA rather than just A. Now what happens is that when the scattering length is negative, you're in the BCS regime where the side of the pairs is much larger than the interparticle spacing, whereas on the other side, as soon as the scattering lengths become positive, it's energetically favorable to create a bound state, and now the size of the pair is much smaller than the interparticle spacing. So that's the two extreme. We have either Fermi liquid here or a Bose liquid here, but it's like weakly interacting. And in the middle, when the scattering length diverges, we are in the unitary point. So that's the one we are interested in. But I will like dedicate two slides later on.
Sorry to interrupt. What is A in this context?
I think there might be a
Uh,
problem. Oh,
oh, a problem? Oh, unstable connection. Can you hear me now?
we can hear you now. Yeah, yeah, sorry.
Oh, okay. Oh yeah, I'm on my phone. Okay. Yeah, so the scattering length, you can vary it by varying the magnetic field in the lab. So it's very interesting. And it's not a phase transition, it's really a continuous crossover. So, because we're in the S wave pairing, so we don't allow any angular momentum between the fermions. If you allow angular momentum, then it's called P wave pairing, and then it's a phase transition. But here it's really continuous, so the ground state is described by the same wave function. So that's uh, really interesting. And so, as we said already, as we lower the temperature, we will go into a superfluid state on both sides. So here you have a plot of the temperature in unit of the Fermi energy as a function of this dimensionless parameter. So T star is the pair formation. And so we see on the BCS regime, you're going to start creating Cooper pairs and they will directly condense into a superfluid state. On the opposite side, you will already have those pairs because they create as soon as you turn on this scattering length, and you need to lower the temperature below this 0.2 of the Fermi energy to really reach this superfluid states. And in the middle, we have our special point, which is a unitary Fermi-gas, but it just belongs to the same picture. And from now on, I will just refer to this blue part. We will be in the superfluid state, no free fermions, and that's really what interested us. So the answer to my first question is not the microscopic component of all the systems, it's more the collective microscopic property of superfluidity. So here you have a plot of the critical temperature depending on the type of system you're looking at. And so I really like the analogy between neutron stars, where the critical temperature is really high because it depends on the density of your neutron star, which is usually high. But it is believed that inside a neutron star, you are in a superfluid state. So we are below this 10 to the 9 Kelvin. But we can learn about neutron star property by doing the experiment in like cold atom experiment in the lab because they're just like studying superfluid. And so that's the universality of this picture. So what is this unitary Fermi gas? Because actually it is this belief that the neutrons also naturally sit at unitarity because the scattering length is way larger than the range of interaction. So that's really an interesting phenomenon. So as we said, it is defined as a scattering length going to infinity. That's really the unique property that's define this unitary point, and this has several consequences. So the fact that the scattering length goes to infinity means we are losing one scale associated with the interaction between those fermions. So now the pairs is of the same order as the only scale that we have in the system left, which is the Fermi momentum. And so we are in a strongly interacting region because every fermions feels every fermions over very large distances. So it's a strongly interacting theory, and it's called unitary Fermi gas because the cross-section reaches the maximal bound set by quantum mechanics, right? So there is an upper bound, and when A is infinite, we reach that bound. So the fermions scatter as much as quantum mechanics allows, basically. We also have scaling variance because the only scale is the Fermi momentum, or equivalently the density of your superfluid. And so it does not depend on which scale you look at the system. And this is a scaling variant theory with some universal property. Here I have written a few parameters. So the Birch parameter, which is a ratio of an interacting Fermi gas by a non-interacting one. It was measured in cold atom experiment, and now it really matches Monte Carlo simulation. So we really a bit more sure about this value. You also have the critical temperature. So that's, for example, what we used to plot the previous previous graph, and unit of the Fermi energy, and also the speed of sound at zero temperature that actually depends on the Birch parameter. And the speed of sound is fixed by symmetry in your system. You don't really have a choice for the form of the speed of sound. And the symmetry here is a non-relativistic conformal phase series. So scaling invariance in this situation implies conformal invariance. And this unitary Fermi-gas belong to more general theory that we call non-relativistic conformal phase series. And so if you know a little bit of conformal phase series, there is an analogy. So the symmetric group is Schrödinger group. You have notion of primary operator, state operator correspondence. And so on the series side, it's a system very interesting to study. Okay, so far it was very general, applicable to all the system I said before. Maybe we can start measuring stuff, and so we will go more in the direction of cold atom experiment. And in particular, we are interested in computing the dispersion relation. So we are in a superfluid state. So we have a spontaneous symmetry breaking of the U1 symmetry of the particle number, and we know we're going to have a Gaussian bus in a massless mode, and the fluctuation of the phase of the condensate is associated with this phonon. So that's the physical quantity we will study. And in particular, we want to study its dispersion relation. So since it's a massless mode, we know it's going to start linearly with a slope that corresponds to the speed of sound, so the one that we showed before. So this is fixed. We don't really have a choice, but we can study correction on top of this linear behavior, because if we introduce a perturbation that is high energetic, like we can have a cubic correction, and the sign of this cubic correction is very important because it tells us about the relaxation mechanism in the superfluid. So if it's positive, it will be more three phonon interaction. If it's negative, it's four phonon interaction. And so the goal is to measure it experimentally and also to compute it theoretically to make prediction about the sign of this cubic term. So there is an experimental paper that did exactly this. So this is the archive number. So let's assume that they've trapped all the atom, well, they confine the atom, they cool them down, and they tune the scattering length to infinity. So we'll not go into detail of that, but this is the sort of condensate they obtain. So they try to have an homogeneous condensate, so it does not depend where you are. So the measure is not it does not depend on the location, and this is just a cut. So it looks like a box, and this is the ZY plane of the density. And so they also use lithium-6 atom, and that's the 2-hyperfin state. It's like spin up, spin down, if we want, with a few property for this condensate. And we see that the temperature, before the critical temperature, it was 0.16. Here it's not that much below, but it's still in a superfluid state. So how do they introduce perturbation in this system? They use Bragg spectroscopy. So it's based on two incoming lather. And the idea is that your superfluid will absorb a certain photon of a certain energy and re-emit another one, so that the total perturbation has energy omega 1 minus omega 2, and the transfer momentum is k1 minus k2. So we are looking at the dispersion relation, right? So we want to probe different momentum, and this is doable by modifying the angle between the laser or equivalently the distance between the laser and the setup. So here you have, as a function of the distance, different wave vectors. So you can see that for very short distances, you have lower transferred momentum. For higher distances, you have more energetic fluctuations. So the question is, what is the probability to excite the system at a certain energy omega and momentum q? So you cannot excite the system in any combination. You really need to probe the excitation spectrum. And this probability by Fermi-Golden rule is proportional to this S function that we call the dynamic structure factor. And this dynamic structure factor is related to the heating rate. So since you give energy to the system, you have a non-trivial heating rate, and they can really extract from this heating rate the dynamic structure factor. That's the one we are interested in because it peaks exactly along the dispersion relation. So here you have a plot of S, and it's omega as a function of Q. So you really see if it's dark blue, it peaks along the red curve that we understand as the dispersion relation. And the dotted red line is the pair breaking continuum. So above this, you're giving too much energy to the system that you start breaking pairs and you end up in a continuum. So we are not interested in this, and we only consider the linear stuff plus the deviation. And in this particular experiment, they found a negative correction. So for phonon processes, as we said, and some people, well, they did not really criticize, but they commented on this result because, first of all, it's not absolute zero temperature, so temperature can influence the sign, and this number is quite small, so it's really easy to make a mistake. Also, the presence of a trapping potential can influence the sign because it's not a homogeneous system, and also the fitting range of Q was really small. So it's already impressive to have an experiment that can measure this cubic term, but there are some effects that needs to be taken into account. And in particular, this is where the theory enters, and we need to really compute this cubic term. So in the theory, it's challenging this unitary Fermi-gas because it's a strongly interacting conformal series, so all the perturbation techniques does not apply in this case, and one is to use large N or effective field theory, and that's the one we will use in particular to study the effect of the potential. It is actually easier to use large N to study the effect of the temperature, but this we will not compute. So the effective field theory is built from the lowest, the low energy degree of freedom, which is the Gaussian boson, as we said. So that's the Gaussian field, where we have the classical ground state, and on top of it we have fluctuations. So pi is exactly the phonon, it's the fluctuation on top of this ground state. And since we study perturbation, dispersion relation, that's exactly the guy we want, the phonon. And so we can build a Lagrangian that is invariant under the symmetry of your system, so Schrödinger symmetry, up to some coefficients, C0, C1, and C2, which are the Wilsonian coefficient that we cannot determine within the effective field theory. We need either large N or the experiment, because, for example, C0 is related to the Birch parameter I told you about. So if you measure the ground state energy of your system, you directly can extract C0. C1 and C2, they appear as combination always. I'm not sure there is an observable that determines C2 only. So that's the most general Lagrangian you can build. You can understand the first term as being the pressure of your superfluid, and then you have higher order derivative or more momentum, power of the momentum, and here we will stop. So I will call C1 and C2 the next to leading order effective field theory, and this is the leading order effective field theory. And since we are interested in fluctuation, we need to expand this Lagrangian quadratically in the field, and that's the propagator of your phonon. And so I cannot explain all the details, but since you're in an effective field theory, it's really important to understand scale in the system. So the high energy scale is the chemical potential, so the delta of before where you start breaking pairs. And the low energy scale is set by the ratio of the chemical potential and the radius of your cloud. So this radius is fixed by your potential. This is where the density of charge vanishes. And basically you have two very distinct regimes. The high energy regime, where you need to include more effective field theory terms, and in the low energy regime where you need to just consider the leading order effective theory, so the pressure term. And the idea is that in both regime you can solve your equation of motion and find the phonon-field. You can also find the spectrum, and you can compute the dispersion, the dynamic structure factor from it. So you were going to find that the dynamic structure factor peaks exactly along those two curves. So in the high energy regime, we found that the combination here is always positive, and it actually does not depend on the potential. It only depends on the Wilsonian coefficient, so the one that the microscopic coefficient that you need to determine with the experiment. And from the known values, this combination with the minus everything here is positive. And in the low energy regime, we found a very suppressed correction to this linear behavior. So this is really the speed of sound, by the way, the 2 mu 3 in the square root, this is the speed of sound in our units. And here it's really suppressed. In their experiment, they use k equal 8. So this is really measurable, but very suppressed. If you had a harmonic potential, that would be definitely relevant. And so here you have a plot. Exactly at them, we can have the dynamic structure factor. So it would be suppressed here linear and then convex instead of concave. And that's exactly the 3D version of this one. So the red curve would be along here. That's what we mean. Okay, and so this was for the spherical case. So if we have a spherical symmetric potential, but to be closer to the experiment, we can consider a cylinder box at the head. So potentially the transverse direction, hard wall in the z direction. And so what we found is exactly the same correction in the high energy regime, which makes sense because it did not depend on the potential. So it's good that we don't see the geometry here. But in the low energy regime, it does depend on the potential. And in particular, we have the longitudinal and transverse mode that are separate now because the system is not isotropic, right? Because we are in the cylinder with, again, a very suppressed correction here. So if you said k equals 1 for the harmonic potential, this is again the leading one. But now it's a combination of transverse and longitudinal modes. So in the experiment, they claim that this is all isotropic, but in theory, having a potential and having a cylinder does not imply isotropy. So I need to be careful. And if we set k is equal 0, meaning that we really excite radial modes, the correction here could be negative but suppressed. Okay, so that's all for the unitary Fermi-gas. So I hope the idea was this is really a universal system that is applicable for neutron star cold atom, even though they look very extremely different. We can compute the effect of the trapping potential using the effective field theory. We unfortunately did not find the same result we found in the high energy regime, which is probably the regime that probe a positive correction instead of a negative one, and this does not even depend on the potential. Temperature is a bit more tricky. You need to use large N and compute two loops corrections. But well, that's the framework. And possible direction for this effective theory would be to consider the ellipsoid. That's even more general, and you can also make predictions of finite temperature, but you need two loops computations. Okay, so I have backup slide for the theory if you want, because this was really short.
No, that was very nice, actually.
So I don't know how understandable this is, if it's too fast on the last part, but it's already 40, so I don't know if I have more time to explain the details.
No, I think it was quite well paced, actually.
Okay, well I can keep it like this then.
How much of the backup slides? I'd be curious to hear through it.
I have all of them from the previous presentation, but then yeah, I could explain a bit more the scale hierarchy, how we really defined how we found it. So if you expand, I don't know what you want to do here.
I mean,
Oh, I'd
maybe
just
if
be
people have
interested to,
questions,
yeah.
otherwise,
Yeah, because then I have really all the details, but
I don't have any particular important in questions, so I'd be happy to listen. But if anyone else has questions, yeah, please ask.
well, I could. Okay. Now, I guess maybe the important step is how you define those scales. So you define that's how you define the classical radius. That's the density of charge, and you ask it. So you want it to vanish on the boundary, right? That's define your radius. So if you have a harmonic potential, you can solve the classical radius. Here that the expansion, as I said, of the action quadratically in the field. And in order for the expansion to be consistent, this needs to be of the same order, and that leads to a hierarchy. So this one is leading compared to the two, C1 and C2. They contribute at the same order, actually. Maybe that's not obvious. But for this, you need the following scaling. So eta control the effective field theory. So adding more eta power, this is how we control the effective field theory C1 and C2. And to find the WKB parameter, you need to compute the equation of motion and see that you have the derivative that comes with this power. So this is really the definition of WKB. You need a small parameter in front of your derivative, and that's how you identify your WKB parameter. Because we're gonna make a WKB ansatz for the phonon-field, and that's what control it. So yeah, that's the WKB ansatz in power of delta. So yeah, that's the leading order, the linear regime. That's why we found the speed of sound. And if you include more term, you can find more corrections in the low energy regime. But yeah, then you have all the computation for the phonon-field. So this is really your field. So you ask for regularity this is 1 in unit of the classical radius. So this is really the end of your cloud, and that's the center. But WKB is always divergent at the endpoint, so you need to fix this. And by fixing this, you get a quantization condition. So that's the. But yeah, then you can play the same game, adding more terms, solving the equations. You get correction to your field, correction to your spectrum. And maybe I can explain the dynamic structure factor. So it's really this definition. So the Fourier transform of your charge density. And the charge density you can find because it's the conjugate of your field. So if you know the field, you know the charge density. And by Fourier transform it, you can find by saddle point this. And we're really interested in where it peaks. So we don't really care about the detail. We want to know along which curve it peaks. And so this is determined by where this guy is 0. And so we can solve, right? So that's going to define exactly the curve along which it picks. So I don't know if how clear it is. This is why I cannot go into too much detail because, yeah.
yeah, you did a good job of sweeping the complicated
Yeah.
stuff
I just
under the
saw
rug.
the results and then they have to trust me. Yeah.
I think that was very
I have a
nice.
question about, say, like the phase diagram you had earlier.
Yeah.
So yeah, did you compute this yourself, or oh no, this is from a paper. I see.
Yeah, that's the reference.
I see.
Yeah, if you look for BCS-BEC crossovers here, you will find this is really, really known and
Hmm.
yeah.
I wonder, do you know how to actually compute this? Because like this isn't using a field theory, is it? Or what sort of the setup they have? Are you aware?
For the when we study the temperature, the critical temperature, you can find it. It's where the other parameter vanishes. So I don't know, within large N you can compute it. For example, we had this value, but I guess you can just vary now the scattering lengths and find this curve. But this is
I
defined
see.
as when the order parameter vanishes. So
Yes, yeah.
yeah. So depending on your framework, I guess the computation is different, but large N is really doable.
Yeah, okay.
So on this graph, which is the exact axis that you're computing across? It's at a fixed temperature, right? Or
Yeah, so in the EFT we worked at zero temperature, so really here, at unitarity and zero temperature here.
right.
Right, but in the experiment though here, so that's why computing the temperature effect is really
Okay,
important.
okay.
They're really close to the critical one. But yeah, in the EFT, otherwise I would add another scale, but I guess it's also doable.
So you wait, okay, yeah, so you're working at a fixed KFA, right?
Yeah, at
Okay,
unitarity.
okay. Right,
So,
right, right.
so yeah, really in the EFT we don't have this parameter and we don't have temperature, but both of them are, yeah.
Okay, okay. So there's like secretly another sort of axis
Yeah, you can really add a
that you're
term that
sort of
takes into
studying.
account
Yeah.
this. Yeah. Yeah.
Okay.
So I don't know, maybe Largen is easier to include these scattering lengths because you just don't drop the Stratanovich coupling, like the sigma sigma term. Because when you send A to infinity, it just disappear. But if you keep it, then you directly have A in your computations. And the effect of temperature is appears when you compute loops because it comes from the sum over the Matsubara frequencies, and that's how the temperature appears.
Speaking of which, you said you needed two loops for temperature. Do you have any ideas why that is the case? Like what happens at one loop? Why can't you take that as
Yeah,
the
the
first
problem
order
with
connection?
temperature is that you have okay, so we looked at large N, and so you have the fermions Matsubara frequencies because you integrate the fermions over, so you need to sum over the fermions loop. But you can also create phonon loops, but the order at which you count is different. So if you only compute one fermion loop, it's suppressed compared to one phonon loop. And actually one phonon loop is like two, I don't know if I can um so you can have your phonon propagator and let's say, I don't know, I need two different. So that's your propagator, and you can compute a one loop correction, right? That's what you do when you expand the field quadratically. But this is a fermion loop, the one that you've integrated over, and this is really suppressed, like this exponential of minus beta something. So what the dominant effect is a phonon loop. This is all phonon field. But basically every vertex, since you have integrated the fermions, is like you have fermionic loop here. I don't know if it's key. Okay. And this is dominant. This loop goes like polynomial contribution. So that would be two loop in the in the fermions.
Oh, I see. Yeah, that kind of makes sense.
Right. So yeah, you need to compute one vertex, another vertex which is the same, and then you need to integrate over this connection. Yeah.
But why can't you just have one a phonon loop without the little fermion vertices or fermion
Oh, you
loops
can
around
do
the
this. It's just
vertices?
that we did in large
Oh,
N. So in large N, the three phonon vertex, it's implicitly depend on this loop. But within the effective
oh, okay.
theory, actually, there are some people that done it, and yeah, you just need to to compute this one loop. Because within the effective theory, by definition, you don't have those fermions. So yeah, you could do this. But then you need to use the EFT.
I see, I see. Was yours okay? Maybe I'm a bit confused about things. The setup is a EFT, but are you talking about a different EFT to do these calculations without the fermions, or is it the same EFT?
No, without the fermion, that would be the same EFT here, yeah.
Okay.
It's just that we looked at large n, but in the end, maybe the effective theory would be easier.
Oh, I see that. Okay,
So
that makes
large
more
n,
sense.
you have those functions integrated, but they are somewhere.
Yes, I see. Okay.